understand the impulse not to be out and about this morning. So this week, I don't know if it will take all week, probably not, but we're going to look at trig metric substitution. This is another integration technique, and I think it's fair to say that it's not most people's favorite technique. It's extremely technical and sometimes requires a lot of messy algebra, but it shows up, well, just like inverse trig functions, as a matter of fact. It tends to show up when you're working with geometric problems where you've got right triangles. So the textbook just presents it, but that makes it look like like a magician's trick. Let's try to see where the ideas behind trigonometric substitution come from. And let's start with an example that we could do without trigonometric substitution. I mentioned inverse trig functions. I said they both tend to come up when we've got right triangles. This is something we could solve or find using inverse trig functions. It's an arcsine problem. But let's try approaching this from another angle. So I keep talking about right triangles. Specifically, this square root, the square root of 9 minus x squared, will show up as the leg of a right triangle that looks like that. So x is one of the sides, one of the legs. That messy looking square root is the other. 3 is the hypotenuse. And now we've got a right triangle. And we say, or we ask ourselves, what can we do with a right triangle? And there are sort of two standard things that we do with right triangles. We investigate them either with the Pythagorean theorem or with right triangle trigonometry. And we've used the Pythagorean theorem. when I drew this triangle on the board and labeled it the way I labeled it, I was using the Pythagorean theorem. This side squared plus this side squared equals 3 squared. So we've used that already. What about right triangle trigonometry? And you'd say, well, you use right triangle trigonometry when we're working with angles, and the way that picture is drawn, none of the angles are labeled. There's no indication that this is a good idea. But I could label one of those angles if I wanted to. I could call that angle theta, and then we could make statements about the sine and the cosine and the tangent and the secant or whatever. And our motivation here is that one side of this right triangle is complicated, whereas the other two sides of the right triangle are simple. And what we would like to do is to use the simple sides of the right triangle instead of the complicated side of the right triangle. So we make a statement that relates the two simple sides of the right triangle. And there are two ways we could do this, but presumably we're more comfortable with the sine than we are with the cosecant. So the sine of theta equals x divided by 3. X is 3 times the sine of theta, and now you see the word substitution in the name. Well, we've solved for x in terms of theta, and we can take this x and we can plug it back in. And if we do this, we're also going to have to replace the dx, but dx works in exactly the same way as when you're, for example, doing integration by parts. We just take the derivative of x and we get whatever we get. And when we write, well, when I do this substitution, when I take this x and plug it in, when I take this dx and plug it in, it's going to, at first blush, seem like we're making things worse. It is not going to be immediately obvious that what we're doing is a good idea. But we get 1 over the square root of 9 minus 3 times the sine of theta squared times 3 times the cosine of theta d theta. So trigonometric substitution, you know, the details vary from problem to problem, but trigonometric substitution all looks basically like this. We let our x be some trigonometric expression motivated by a right triangle. Once we have x in those terms, we find dx, and then we replace x and dx, and we get some mess, or on the face of it, something that's a mess. But trigonometric substitution, I mean, I'm not claiming this is a one-size-fits-all solution to anything. We don't have a bunch of those in the calculus. But what trigonometric substitution always does is trigonometric substitution always can get rid of that square root. And it's usually a problem to have a square root. I mean, if you're not doing a U substitution, it's hard to know what you would be doing. And the reason trigonometric substitution gets rid of square roots is, again, down to the Pythagorean theorem, more or less. I mean, if we look at this triangle and we hit it with the Pythagorean theorem, we're going to square this leg, and squaring the leg will make the square root go away. Let's formalize that. Okay. So we always, I say always, there are a few different trigonometric substitutions. We'll see them all by the end of the week, but we always start by expanding whatever's in the square root. And then whatever's in the square root will always have common terms. So in this case, a 9 and a 9. This is guaranteed to happen by the way trigonometric substitution is done. The way trigonometric substitution is done guarantees that after we pull that common term out, we'll be able to rewrite what we have left as a perfect square. And this comes, I mentioned the Pythagorean theorem. It comes more specifically from the Pythagorean identity. The statement that the sine squared plus the cosine squared is 1. So the cosine squared is 1 minus the sine squared. And again, whatever its sins, trigonometric substitution is extremely algorithmic. It always starts in the same way with the same steps. Anytime we do a substitution that involves a sign, we'll always get a square root that looks something like this. We'll always use the Pythagorean identity. We'll always wind up with a cosine squared under a square root. Let's see, 3 times the cosine of theta d theta. And then we'll always use the fact that we have a square root of a product, and the square root of a product can be broken up. Going to slightly sweep a few technical details under the rug. Properly speaking, the square root of something squared, the square root and the square don't really cancel each other out. You wind up with an absolute value. For technical reasons that we don't really need to get into right now, that's not going to be an issue. The cosine will always be positive. The absolute value isn't going to do anything. And once you've done all of this, it's kind of your moment of truth. Because you can do trigonometric substitution, you can do all of that and wind up with a new integral that you still can't take. And that's obviously very frustrating when it happens. But here, everything cancels. That 3 cancels. That cosine cancels. We get 1 d theta. And 1 we can integrate. And because of that d theta, our variable is not x anymore. Our variable is theta, and the integral of 1 is theta. And then we have, now we take the integral, we have theta now, or we have our answer in terms of theta. And what we do now will vary a little. We're no longer in the pure algorithm stage. We know we can't have theta. Our real variable is x. Theta is just this thing we made up. So the question becomes, well, how can we go from theta to x? And the answer varies. Sometimes you end up using that right triangle and right triangle trigonometry. Here, in this case, we're just going to take that equation and we're going to hit both sides with the arc sign. The sine of theta is x over 3. Theta is the arc sine of x over 3. Again, we're skipping some technical stuff under the rug. The sine and the arc sine only cancel if our input is in certain intervals. That all turns out to always happen. It's not something we need to worry about. So the integral is theta plus c. Theta is the arc sine of x plus 3. X over 3, I mean to say. And there's the integral. And obviously a lot of work for something, for a problem that did not require it, for a problem that we could have done just using the arc sine, assuming that we remembered the relevant formulas. But, you know, using the arc sign for this is extremely delicate. Like, to use the arc sign, I mean, stating this more explicitly, we need a 1 up there. Or if we have a constant other than 1, that would be fine too. But if we had a variable up there, the arc sign wouldn't work. Like if we had an x or an x squared or an x cubed, for example. Trigonometric substitution can work even in situations where the arc sign doesn't. And I'm going to state the first of 3 sort of guidelines. If you see the square root that looks like this, you might try a trigonometric substitution like that. And if you try this, you should be picturing a triangle that looks like that. And you see the word might there. I mean, I've already mentioned it's, of course, certainly possible to do trigonometric substitution and wind up with a new integral that you still can't take. Or it's perfectly possible that you can see this square root and trigonometric substitution is still not the thing to do. You know, here we see the square root, and trigonometric substitution might work in the end, but there's a much more straightforward way to approach this, which is what?
We could make 9 minus x squared to u.
Yep, u substitution. So trigonometric substitution might or might not work out, but it's certainly not the easiest way to approach this. The one guarantee that we do have is that if we do this trigonometric substitution, our square root will go away. So because we often don't want square roots, and trigonometric substitution will always get rid of the square root, that's its power, essentially. And these problems get pretty tedious, I'm afraid, but let's work out a problem. Let's take the problem we did and mess around with it. Let's turn that 1 in top to an x cubed, so that just using the arc sign no longer works. Before I do that, let me go back here and just make a quick observation. This is written in terms of squares. And the significance of this is that this number has to be positive because any square is positive. It does not have to be a perfect square. You know, if we have 7 minus x squared, and we tried this trig substitution, we'd wind up with this. We would write 7 as the square root of 7 squared. So the important thing here is that that number be positive. You can't rewrite a negative number as a square. But, you know, just to make everything a little nicer, we work with a perfect square in this second example. So we have this advice. We certainly don't see anything else to try. It's not a U substitution. It's certainly not an integration by parts. So 9 is 3 squared. So here A is 3. And whenever we do this, we need to change dx together with x. And the triangle we should be picturing, let's see, has A here and x here and the square root here. And in the previous when I say we should picture this triangle, we're going to need it at the end of this problem. We're going to wind up with something like, I mean, I forget exactly what, but something like the cosine of theta. And then if we have the cosine of theta, of course, we can't use the arc sign like we did in the last problem, but we can go down here and read off the cosine is the adjacent over the hypotenuse. So that's why we always want to have that triangle in the back of our minds. Okay, so we've got x cubed, 9 minus this thing squared, and we've got dx. So, as I say, nothing very appealing on the face of it, but this will make the square root go away. That's our guarantee. What happens next? We don't know yet. But we're going to make the square root go away, and this always happens in the same way. Specifically, if we square this, we always get the same number out front and then in front of the sign squared. We always pull that number out to get 1 minus the sine squared. And we always use the Pythagorean identity to turn that cosine squared, or rather to turn that 1 minus sine squared into a cosine squared. So, as I say, it's very messy looking, but up to a point, it's also very algorithmic. Every time you do a problem that looks like this, you're going to be following the same basic steps up to a point. So we rewrite what's under the square root. We do not forget that expression, 3 times the cosine of theta, 3 d theta. That top, well, whatever, we can leave it as it is for the moment. The bottom, the square root always goes away, and it always goes away in precisely the same way. You have the square root of a product. The square root of a product is the product of the square roots. This first square root is always exists because we have a positive number. And our square root vanishes. And now we're in kind of, now we're just sort of doing our best. I say this is algorithmic up to a point, and that point is now. We always get rid of the square root. It always happens in precisely the same way. But as for what happens next, well, I mean, it's perfectly possible that that we wind up with an integral that we can't take. But in this particular case, that is not the case. We have cancellation here. And we have that, that thing on the top, which I am now going to rewrite as 27 times the sine cubed. And that 27 is no big deal. That 27 we can just pull out. The sine cubed. This problem is still putting up a fight. But we have an odd power of the sine here, and that's hopefully something we remember how to deal with. We pull that sine out. And now if this were like the sine to the 8th, we'd rewrite it as the sine squared to the 4th. It's just the sine squared. There's no rewrite necessary. We, for the second time, in one problem, use the Pythagorean identity. The sine squared is 1 minus the cosine squared. We now hit this with U substitution. Textbooks, by the way, or like online resources, sometimes just use the word substitution. I've been using U substitution very diligently because we now have 2 types of substitution we can do. We're missing a negative, but we can think of that as just missing a constant, like you can put a negative sign there and a negative sign there and balance it out. So we've got negative 1 minus U squared du. Negative 1 minus U squared du. Wait, incorrect. This negative sign is part of the du. So we have positive 1 minus U squared. But we're coming to the end of it. U minus 1/3 U cubed plus C. So the cosine of theta plus, let's see, that's 9. The cosine cubed of theta plus C. And we're still not done. Because I mean, what's a theta? Theta is just some dummy variable we created. So just like when we do U substitution, we cannot wind up with U. When we do trigonometric substitution, we cannot wind up with theta. When we do U substitution, getting rid of the U is a very straightforward thing. When we do trig substitution, that is not the case necessarily. No, we had x equals 3 times the sine of theta. Doing the trick we did if it's the last problem is useless to us. You know. Or rather, let's say that doing this gets us an answer written in a way we do not want our answer to be written. We really would rather not have a cosine of an arc sine, for example. Well, I already sort of gave away the trick here, which is that if we think of that right triangle, we can see what the cosine is using right triangle trigonometry. The cosine is the adjacent side over the hypotenuse plus 9, and once again, the adjacent side over the hypotenuse. This time it's being cubed plus c. And you could do a little work with this. I mean, that -27 and that 3 in the first expression cancel. In that second expression, we could, rewrite that denominator as 3 cubed is 27, and then it will partially cancel with the 9. But this is, the calculus part of things. So that, I wish I could say that that's trigonometric substitution. That's 1/3 of trigonometric substitution. Going way back, not that way back. You see this statement. If you see a square root that looks like this, you might try doing such and such a substitution. Well, there are 2 other statements for 2 other trig functions and 2 other square roots. I mean, the good news is that, once we have the idea, this idea transfers smoothly. Like, all of the trigonometric substitutions are going to give you a square root, which you'll rewrite, and then you'll use the Pythagorean identity to simplify. So they all work the same way. So I say we're 1/3 of the way done, but really more than that, because once we've seen this basic idea, it will transfer to other substitutions. So with 8 minutes left, I won't do a substitution. I'm going to just quickly do a problem from the test, maybe kind of futilely, because I think all the people in the room might have gotten it correct, but on the exam, I asked you to integrate the tangent, and I did not, I sort of gave you a hint. Instead of just saying, here's the tangent, go at it, I pointed out that the tangent is the sine over the cosine. And most students recognize this as a U substitution problem. But I had a fair few students try U equals the sine of X. And I just want to talk about that for a bit. If U is the sine of X, then the cosine, then du is the cosine of x dx. And this is not successful. Because the problem is that if we look at this cosine and you look at this dx and you ask what we do not have the cosine of x times dx. What we have is a fraction, dx divided by the cosine of x. So we do not have what we need to make du here. The instinct to use u substitution is the correct instinct. U has to be the cosine of x. If we want to, formally speaking, dx is just an abstract symbol, but if it helps, you can think of it as dx over 1. And we have sine x dx, exactly what we need. Well, almost exactly what we need, but we can deal with missing negative signs. The integral of 1 over the variable, 1 over u, is the natural log. So yeah, as for how the test went, I didn't bring it, but you've seen your grade book. I think it went well. I've emailed anybody if I had concerns and wanted to talk to them, so I'll return it to you, but if you didn't get an email, then you're in good stead. Okay, I will. Yes, I'll see you tomorrow. It's supposed to be very bad, like -20-degree wind chill, but without snow, my assumption is that